So that tells me that the final exam has to be more challenging, right? So that's easy, so I think that is the feedback you have given me, through the exam performance. But I'm happy that your batch is continuing to perform at
And sir, mostly thanks to you only, sir, because you are restricting, you are allow us to study only 13 videos. That is why we are able to concentrate more. And rest of the subjects are, so 32 classes, around 19 is there, sir. So we need a lenient then.
Okay. I think we have completed close to 18, 19 lectures, but we decided 2 weeks ago that we will stop there, right? So
Yes,
I think
yes.
perhaps that may also play a role. But so for the final exam, the syllabus will be from where we stopped to the end. So
yes, sir. 14th class, 14th to 32. That is what.
All right. Okay. Fine.
Right, sir.
Okay. So let's get started with today's class. So today we will get started with analysis in the state space domain. So microphone is on. Let me see. Yeah, Roshan, can you mute your microphone?
I'm sorry, sir. I'm sorry.
Yeah. Vigneshwaram also. Some echo was there. That's why it's. So, yeah, as I was saying, last class, we were looking at the state space representation. The state space representation for the class of systems that we are studying is x dot equals ax plus bu, y equals cx plus c dot x plus du. So as we observed previously, the advantage that you and I get, by going to the state space representation, is that point number one, we stay in the time domain, and point number two, we are also able to rewrite an nth order ODE as n first order ODEs, right? So consequently, the order of the ODE is only one, so it becomes easier to solve it philosophically. But then the issue is that the ODE is now become a vector ODE. Okay, that is, we can see that we are having the state vector, whose derivative is appearing, and also a matrix, right? State matrix which is appearing. Okay, so then the question arises: what do we need to do, right? So we need to learn a little bit of linear algebra, okay, and matrix theory, which we are going to do starting today, so that we can appreciate how control design is done using state space. Okay, so a little bit of theory is necessary, and that's what we are going to learn. Okay, and importantly, we also looked at this equivalence between the state space representation and the transformation representation, right? P of S was C dot Si minus A was P plus D. So consequently, the place we stopped was it I requested you to check it out for the mass spring damper system. So I hope you had a chance to do it. But if not, that's how we start today's lecture. So for the mass spring damper system, the matrix A, if you remember, was 0, 1 minus K by M and minus C by M. So consequently, Si minus A comes out to be this. And as we discussed, the inverse of a matrix is the adjoint of the matrix divided by its determinant. Now, how do we get the adjoint of a matrix? I'm sure you would have studied in some engineering math course, also in some other course as part of your MTech. How do we calculate adjoint of a matrix? We form what is called as a cofactor matrix and transpose it, right? So cofactor matrix is obtained by hiding the ith row and j column for the ijth element and taking the determinant of the remaining n minus 1 by n minus 1 matrix, right? So that's how we calculate the adjoint. For a 2 by 2 matrix, right, it becomes pretty simple. What we do is that, to get the adjoint, we swap the diagonal terms, and then we also swap the off diagonal terms, but then multiply them by -1. Okay, so that's how we calculate the adjoint, sorry, the cofactor matrix. And then we need to take the transpose. Okay, so the adjoint comes out to be this. So an easy way of remembering the adjoint for a 2 by 2 matrix is that we swap the diagonal terms and multiply the off diagonal terms by -1. Okay, so that's how the adjoint comes in. And the inverse is adjoint by determinant. So we get the inverse here. Okay, and if we simplify this formula, which we have learned as the equivalence between the Planck transfer function and the state space representation, C in this case, as we have already written for the mass spin Damping system, it's the vector 1, 0. B, as we know, is the vector 0 and 1 by n. So if we simplify this and we evaluate the result, it comes out to be 1 by ms squared plus cs plus k. Okay, and as we know, 1 by ms squared plus cs plus k is the Planck transfer function for the mass spin Damping system. So what you and I have shown is that we have demonstrated this expression. Okay, P of S is C dot Si minus A inverse B plus D for the mass spin Damping system. Okay, so now if we look at the Planck transfer function, as we know, the Planck transfer function is a ratio of two polynomials in S. Let's say we call it n of S by d of S. And as we have figured out, Si minus A inverse B is also a ratio of two polynomials in S, right? Of course, the numerator polynomial is a matrix form, but still it's a polynomial. It has S terms contained, right? As we have already seen, Si minus A inverse was this, right? We had S plus Cm1 minus K by M, yes, and all that. So the numerator is adjoint of Si minus A, whereas the denominator is determinant of Si minus A. Okay. Now, as we know, if we look at the determinant of the, the denominator polynomial of Si minus A inverse, and we evaluate the roots of Si minus A, the roots of any polynomial we get by solving that polynomial equal to 0, right? All of us know about that. So when you and I solve Si minus A equal to 0, the polynomial is, we solve determinant of Si minus A equals 0. Sorry, there's a typo here. Okay, you and I need to solve determinant of Si minus A equals 0, and that is the denominator polynomial equal to 0, and determinant of Si minus A equals 0. If we solve it, we get the eigenvalues of the state matrix. How? If we recollect the definition of eigenvalue and eigenvector, last class we discussed it, right? If we take a matrix A, lambda is the eigenvalue and V is the eigenvector, provided V is not 0, such that AV is equal to lambda V. Okay, from that equation, we got determinant of lambda I minus A equals 0 as the equation that you and I need to solve to get the eigenvalues lambda. Okay, so that is the definition of eigenvalue, and that is the formula for calculating eigenvalues. Now, we observe that lambda, S are all anyway complex variables. Okay, it doesn't matter which one we use, right? So, so consequently, what happens is that like the denominator polynomial, right? What happens in this particular case is that like we have determinant of S minus A, and when we solve the roots, we get the eigenvalues of E. Now, if you look at the left-hand side of this equation, the denominator polynomial is D of S for the Planck transfer function. And what are the roots of D of S? As we have already studied, they are the poles of the transfer.
Poles, yes.
Correct. So on one side, we have in the denominator, left-hand side, we have the polynomial D of S. Right-hand side, we have the polynomial determinant of S minus A. So obviously, when equality holds, the roots of the two polynomial also should be the same. So, but we will shortly see that there is some more condition. We need to satisfy what is called as a minimal realization. We will come to that later. But in a broad sense, this provides us with a broad rationale as to why the eigenvalues of the state matrix and the poles of the transfer function are by and large the same. Okay, right? So essentially, this is an important, I would say, requirement, right? So the point is, why is this important, right? So for what purpose did we use poles as a transfer function when we did control design, also systems analysis? What role did poles play?
To define the stability of the like control system.
Right? So we wanted to essentially figure out whether like we needed to have poles. We wanted to figure out if a system is stable or not. For that, you and I looked at the location of the poles, right, of the system, right? So that's the importance of poles. So now we can immediately realize the importance of eigenvalues, right? So we also discussed in between when we discussed stability, right? So the eigenvalues of the state matrix also play an important role as far as stability of the system, and we use the state space representations. So we can immediately observe that for specific cases, we have poles of the system transfer function and eigenvalues of state matrix, right? Becoming one and the same. All right. So that's an important result for us. All right. Okay. So now, as I mentioned, when we use a state space representation, we essentially stay in the time domain, which is good. But then, we have to solve an ordinary differential equation. It is a first order differential equation, right? X dot equals ax plus bu. But it is a first order vector ODE. Okay, so you and I need to know a little bit about ODEs and also how to solve vector ODEs. Okay. So
sir,
yes, please.
Sir, I have a question over here. I'm sorry to ask this question to you, but because one thing, sir, basically eigenvalue, sir. You use the word like it scales the, like what I mean to say is when we the meaning of eigenvalue, that while explaining that concept you use the word we are scaling something, right, sir, if I'm not wrong. So sir, basically, sir, how to represent that in a like I would say representative manner, like by image or something? If you can just make us understand, it will be great. I'm sorry to ask this question beyond topic, but still request, sir.
This is a very special interpretation, Roshan. Let's say you take a two-dimensional space. We will look at it later. Let's say we have two-dimensional space. Let's say you have vector. Okay. So an eigenvalue lambda can either scale up this vector, scale down this vector, or scale up this vector. Okay. So if you visualize a vector as one which is represented by a directed line segment, okay, what we call as an arrow, right? So an eigenvalue can scale it up or down, or it can also change its direction if it's negative. Okay, that's a very simple graphical visualization of an eigenvalue. Okay? And this arrow, which denotes the direction, is the eigenvector. Okay, so that is the basis of a graphical interpretation of eigenvalue and eigenvector. But this is only a specific case, and we will interpret more as we go along. Okay, because eigenvalues are going to become very important for stability as far as state space representation is concerned. Okay?
Thank you so much, sir. Thank you so much.
So now, going to ODEs. So by the way, I think yesterday all of you mentioned that you are yet to do your computational engineering course, right? Am I correct?
Yes, sir.
Okay. Okay. So in fact, if you had done that computational engineering course, you would have revised a lot of things about matrices, vectors, and eigenvalues and eigenvectors. Okay. So did you study anything about all this matrix theory in any of the other courses that you have taken till now?
1 minute,
So there was a bit of mention in optimization classes while,
Okay.
but like,
This
but not to the depth. Like what I meant to say is this was just a mention in that sense, and we use some of the basic concepts of like matrices and all this in optimization classes.
Okay. So, so anyway, so we will we will anyway learn what is necessary for our course. Right? So why did I ask that? Because like solving ODs is a very important aspect. Particularly when we go for computational classes. In fact, let's say we start with the first order OD. Okay, x dot equals axt. Okay, where a is a real number. So this is what is called as a linear first order homogeneous ODE. So it's linear because it's linear in the variable x. Okay. It is first order. Why? Because the order of the highest derivative of the variable is 1. Okay. And why do we call it as a homogeneous ODE? That's
Because we don't have any like constant. What I mean to say is mx dot mx double dot plus cx dot plus kx. Sorry, kx is equal to something is not there. It's like 0 in that sense. On the
so
right hand side is 0.
Okay, very good, Roshan. In fact, that's the exact answer I was waiting for, right? So, but then, Roshan, you can immediately see here the right hand side is not 0, right? Well, then why am I calling it homogeneous?
So, but we can take it left hand service because it's a variable of x only.
So, the interpretation that you correctly gave was that if you connect all the terms involving a particular variable to one side, okay, which I have done here, right, where we have taken all terms involving x to the same side. If the right hand side happens to be 0, then we have a homogeneous ODE. Okay. So, in fact, the correct way to look at homogeneous ODEs is that there is no forcing term or forcing function. Okay. So you can see that even when you take mx double dot plus cx dot plus kx equals f, right? F is the forcing term, right? That is why it's an homogeneous ODE, right? But if f is 0, then we'll have only mx double dot plus cx dot plus kx equals 0, right? That is a homogeneous ODE. I hope the physics behind homogeneous ODE is clear, right? Once we understand that, the mathematics becomes simple. All right. So you take everything to the right hand side becomes 0. Okay. That's how typically, we explain homogeneous ODE, but I hope the important difference is clear, right? Okay. Now, this is a first order homogeneous scalar ODE. And if we solve this ODE, you and I get x of t to be equal to x naught e power at. Okay, where x naught is the initial condition. Okay, so this is a well-known result. This is a very simple result. Okay, and we get this a solution for x. Right now, we have vector ODE. Right. See, similarly, when we consider the state equation, right? What was our state equation? It was x dot equals ax plus bu. Now, if I were to consider the homogeneous version of this, what should I do? There should be no forcing term, right? Here, what is the forcing term? Forcing term is the input u, right? So that should be equal to 0 for homogeneous ODE. So the homogeneous vector ODE, first order vector ODE is x naught equals ax. So that's why we are considering this to be the linear first order homogeneous vector ODE. Okay. Now, if we want to solve this equation, okay, you and I use Laplace transform. Of course, we don't take 0 initial condition because we are not finding the transfer function. We are only finding the solution to non-zero initial condition. So finally, we get the solution x of t to be some function phi of t times x0. We'll figure out what this function phi of t is. Phi of t comes out to be Laplace inverse of si minus a, right? At first glance, this looks a little bit complicated, okay, but we are going to deconstruct it and make it very simple. Okay, so this is what is called. We will shortly see that this is what is called as a matrix exponential. Okay, so we will be learning all those things shortly. Okay, So in other words, what we are telling is that like the solution to the first order, vector ODE, x dot equals axt is going to be phi of t times x0, and phi of t is nothing but Laplace inverse of Si minus A inverse. Okay, so that's the, so what we need to do to find phi of t is that we calculate Si minus A inverse, and then like we take the Laplace inverse of Si minus A inverse. Okay, then only we can get the let's see, solution. All right. So there is another term which we are going to shortly show that Laplace of Si minus A inverse is e power at. Okay, where e power at is so-called matrix exponential. Okay, so what is this matrix exponential? We would have learned some properties about matrix exponentials. All of us are familiar with exponential functions till now, right? So you and I would have also looked at it when we studied about transfer functions and getting solutions of ODEs, right? We would have encountered the term e power at, where A was a real number. Okay, so this was a real quote unquote exponential. But however, now we have a matrix exponential. So what is this matrix exponential? We have the same exponential function, but the exponent now is a matrix. Okay, so A is a matrix. So I hope this intuition is clear, right, on what is the difference between, the scalar exponential and the matrix exponential. It so turns out that the matrix exponential satisfies all these properties. Okay, so once again, this I have given it only for information. And similar to a scalar exponential, we can calculate a matrix exponential by expanding in terms of a power series. Okay, which is what we have done this. So please note e power at, right? When we look at it, it is 1 plus at plus a squared t squared by 2 factorial and so on, right? So similarly, e power capital At, okay, which is the a matrix exponential, where A is a matrix, you and I can expand using the same formula, but instead of small a, we substitute capital A, okay, where capital A is the matrix, okay, state matrix. Okay. So once again, we need to learn all this theory so that finally we can come to the physical problems using the state space representation and start applying this. Okay. So I hope broadly the matrix exponential is clear. Okay. Now, so now what do we do with this matrix exponential? So it turns out that we can show that this matrix exponential, this is the derivation here, okay, is in fact equal to the Laplace inverse of Si minus A, okay, which we called it as phi of. Okay, so that's what you and I would have shown here using the properties of the matrix exponential and also properties of the Laplace transform. Okay, so we would have shown that this is indeed the case. Okay, now the point is, we have e power at, which is a matrix exponential. It is what is called as a state transition matrix. Why is it called as a state transition matrix? Okay, I'll explain it shortly. So where did we start off with? We started off with the homogeneous vector ODE, okay, which is x dot equals axt. And we found out that the solution to that is this matrix phi of t times x0, where phi of t was the Laplace inverse of Si minus A inverse. Okay, so this is what we have. Now, what you and I have shown further now is that e power at and phi of t are one and the same, okay, which is equal to the Laplace inverse of Si minus A inverse. So, what all this tells us is that x of t which is a solution to that unforced state equation, is e power at x0. Okay, so e power at due to this reason is what is called as a state transition matrix. So why is it called as a state transition matrix? Please note, it helps calculate the state at every instant of time, right? Given the initial state x0. So you substitute any instant of time, you will be able to get e power at, and you multiply that e power at with x0, you will be able to get the value of the state at the corresponding instant of time. Then we are seeing that e power at helps us to transition from one instant state at the corresponding instant that you and I are interested in. And that is the reason it is called as a state transition matrix. Okay, so I hope the meaning of the term state transition matrix is clear, right? And why it is called the state transition matrix. Okay, so once again, it helps us transition from one instant to another and calculate the state at each and every instant. Okay, so that is the reason we call it as a state transition matrix. Okay, now we have this state transition matrix. Question is, if you and I want to solve a system model, let's say even we consider any problem in vehicle dynamics and we represent the model in state space representation, you and I want to solve for the state vector, right, and do control based on that. The question is, how do we solve for the state, right, x of t? Because x of t is e power at x0, right? So then I need to solve e power at, right? I need to know what is this e power at, right, or this matrix exponential. So calculating the matrix exponential or the state transition matrix becomes very, very important. Okay, and that's something which we are going to learn in tomorrow's class, one of the methods. But however, just to get the discussion started, let's say we have a matrix like A, which is 1, 2, 0, 1, right? If I want to find the matrix e power at, okay, which is the exponential of this, right? It is nothing but exponential of 1, 2, 0, 1 t, right? In a sense, it is the exponential of the matrix t, 2t, 0, and t, right? So one may immediately get a feel that, look, oh, okay, you know what, I will apply the exponential to each of these matrix terms. So I may get e power t, e power 2t, e power 0 is 1, and e power t, right, for t. So is that the way it should be? It's out on the other, that's not correct. Okay, so we cannot calculate the matrix exponential in this manner. Okay, it may be applicable in special situations, but it is not applicable in all conditions. Okay, so there's a big difference. So it so turns out that the matrix exponential cannot be calculated in this manner, okay, for any given matrix. So how do we calculate it is something that we will see in the next class. In fact, we will see that, like you and I need to, like calculate the SI minus A inverse and take the Laplace inverse of it. Okay, so that will give us the matrix exponential e power at. Okay, so that is one way to calculate the matrix exponential, and we shall learn it tomorrow's class. And then we will start using that matrix exponential, right, to start solving state equations and also do analysis of dynamic systems in the state space representation and ultimately for control. Of course, today, once again, just like what we discussed in classical control, right? You and I have digital computers which can calculate these items very, very fast. Okay? So then the question becomes, right? So what do we, do? right? When we essentially want to calculate and then do analysis, right, in the state space representation. Okay? So that's something which we will discuss as we go forward. Like one may also get the question, why should I learn all these things, right? So if I have a computer, right, which can do these calculations pretty fast. So the logic is the same. That is, you and I still want some intuition, right, and understanding of concepts in the state space representation. That's why we will learn the relevant theory, right? Okay. So that's the material we would have seen in today's class. Any questions on this, please?
Sir, one question. Am I audible?
Yes, please. Please.
Sir, I understand this. We are taking the phi of s in terms of exponential matrix, right? EAT. Why does it have to be exponential in nature?
Okay. So once again, like we go, like to the fact what we would have previously discussed, Prem. So you take any mathematical equation, right? When we solve solution to an equation, okay, there are two fundamental questions which you and I have to ask. The first question is whether a solution exists. Okay, so that is what is called existence of solutions. The second question is whether the solution is unique or not. Okay, so it so turns out that linear ordinary differential equations, irrespective of whether it's a linear scalar ODE or a vector ODE, a solution exists, and there is a unique solution, and the unique solution is the exponential function. So when you and I had a scalar ODE, the exponential was a scalar exponential, e power at, right? Was it not? When you and I have a vector ODE, the exponential function is a matrix exponential. Okay, that's all there is, the differences. Okay, I hope it's clear.
Sir, I also understand that because when we multiply in the actual equation, because of the Laplace, it is coming in the exponential nature. That is also the fact, right?
So the fundamental thing is this logic, Prem. Okay.
Yeah. Okay.
So due to this, so in fact, like there are references where there's a long proof to this particular concept. So the outcome of the Laplace inverse being taken and the exponential coming, those are all because of the definition of the Laplace transform and the corresponding property.
Yeah.
So, but the fundamental result is this. Okay, that is when we have a linear ODE with constant. Okay, whether it's a scalar ODE or a vector ODE, a solution exists, and the only solution is the exponential. Okay, so I hope that's clear. Right?
Yeah. Thank you.
Yeah.
Sir, we have, if we take analogy with respect to classical. Sir, am I audible?
Yes, please go ahead.
If we compare and make an analogy with classical method where we have considered unit step and ramp and sinusoidal inputs, the case might be, I was trying to make a point, maybe ignore if it is wrong. The case we can easily associate with sinusoidal input, but how do we make a coronary with respect to step inputs and also, because it's going to be 1 by S, right?
Can you kindly repeat? I didn't maybe I didn't catch the perspective of the question, right? So see, inputs are what they are, right? Irrespective of the representation, whether it's a transfer function or state space. Okay, point number one. So am I correct in interpreting that we are able to analyze step response, sinusoidal response easily in the transfer function representation? Is that what you are trying to say?
It's the other way around. E of AT function we can write in terms of sine and cos, and so it becomes equivalent. How do we?
Okay. 1 minute. Okay, now I think I get the perspective. Please note, e power only j omega t or j something deity, right? You can write in terms of cause and sign.
Yeah.
And please note, in general,
That is approximation.
this A will be a combination of real and thing, right? The real part will take care of the other functions.
Got it, sir. Got it. Yeah.
Yeah. Okay. Any other questions?
Sir, we have to sync a bit in this today lecture. So probably.
No problem.
Yes, sir.
So,
Sir, one request. Can you recommend some a simple mathematical book which can help us to just refer and
Sure. Yeah. So once again, there is a book on linear systems by Ogata. Okay. So again, I forgot the complete name of the book. Ogata has this book, right? I think it's called Modern Control Engineering. Okay. That's a nice book to read. It's also very simple, it's intuitive, and the reason I like it is because it is also written with an engineering perspective. Okay. Yeah.
So thank you so much.
Thanks. So I think Arunachalem, is everyone present today?
Yes, sir. Everyone is present, sir.
Okay. So then I think we can end the class today. Tomorrow, please remember Abhinav in the class. He will share a Google Meet link in the classrooms. Please use that link, not this. Okay. And if there are any issues, kindly contact me. We will meet once again on Wednesday. Yeah.
Sure, sir.
Right?
Okay. Thank you.
Okay. Thank you all. Thank you. Bye.